Hello everyone, my name is Marcos Lage. I'm a professor at Federal Fluminense University in Brazil. I will present a work called A Visual Approach for Building, Managing, and Analyzing Weather Simulation Ensembles at Runtime. This work is part of Carolina Vega's PhD contributions and was developed in collaboration with other researchers from the Federal Fluminense University and the University of Illinois Chicago. Extreme events have become more frequent in recent years, making weather forecasting essential to avoid severe damage. Forecasting is typically performed using numerical modeling, which is powerful but challenging since climate specialists must handle extensive data like satellite images and land description data, for example. To be aware of uncertainties, weather specialists commonly create, manage, and analyze ensembles containing several numerical simulations. The challenges associated with weather forecasting become evident when they fail to detect outlier extreme events, such as the catastrophe in the mountain region of Rio de Janeiro in Brazil in 2011. In this occasion, almost 1,000 people died during a severe storm that was not previously detected by any numerical simulation. Climate specialists handle extensive input data and go through complex steps to perform atmospheric modeling. Generally, the atmosphere is discretized by a three-dimensional grid. Physical equations are numerically solved at each grid point based on initial conditions from satellite and measuring instruments. Some modeling strategies, known as limited area models, require setting up several nested domains with different resolutions to increase the simulation accuracy in smaller regions of interest. However, even high-resolution grids cannot detect microscale physical processes, such as convection and turbulence, essential to weather forecasting. For this reason, these processes are usually coupled to the solutions of physical equations using parametrizations. Weather experts may consider several microscale physical processes in a simulation. Usually, each process has multiple parameterization options available. For example, suppose that the expert wants to consider the four physical processes illustrated in the slides. Since for each process several parameterization strategies are available, it's up to the expert to select one parameterization for each process when setting up a simulation. After setting up the model, a typical simulation solves the mathematical equations and exchanges data with the parameterizations, generating spatial-temporal results for each time step. However, the produced data can be massive when it involves many atmospheric variables, time steps, spatial resolutions, and parameterizations. The challenge increases when the weather expert must handle ensembles of simulations to perform sensitivity and uncertainty analysis. In this work, we used the WRF model, which is widely used for operational forecasting and research. A typical WRF workflow consists of pre-processing and post-processing modules, usually run through command lines. Each module generates an output file that serves as input to the next module. Reusing those output files to carry out new simulations is possible, but this task may become laborious and error-prone if manually performed. Faced with the challenge of configuring, controlling, and analyzing sets of simulations, we propose ProWiz, a visual analytics and provenance-oriented system developed in close collaboration with weather researchers from Brazil. It allows configuring, executing, monitoring, and analyzing individual runs and ensembles of simulations performed using the WRF model. The system meets these requirements: support simulation setup, automate simulation runs, manage provenance data, optimize preprocessing, automate data extraction and management, support the visual analysis of ongoing runs, support the creation of simulation ensembles, and support the visual analysis of simulation ensembles. ProWiz is comprised of a backend and a visual interface. The backend includes a workflow system to manage WRF workflows implemented using the Apache Airflow, a MongoDB provenance and metadata database, and a server core that connects the database and the interface. The server core is responsible for managing runs, storing, loading, and aggregating data dynamically. Please check the paper for more information about the system backend. The interface includes three interactive views. The first one is the setup view. The setup view comprises a top menu, a domain map, a domain summary table, and a parameterization menu. Users can set the simulation domain's grid, resolution, and central points using the top menu, defining the start and end simulation time, and select the ICBC data source. The domain map and summary table allow the visual definition and verification of simulation domain's configuration. The parameterization menu allows the selection of the physical parameterization considered in the simulation. The second view implemented in the system interface is the simulation view, which provides individual simulation visual analysis capabilities. It contains a top menu and three panels: the Runs Overview, the Temporal, and the Spatial Analysis panels. The top menu allows the users to configure the currently selected run, the grid resolution considered by the visualizations, the function used to compute atmospheric fields aggregations over time, and up to 3 atmospheric variables of interest to be jointly analyzed in the spatial dimension. The Runs Overview panel enables monitoring active simulations and the creation of new simulations that share configuration parameters with previous runs. It is composed of a graph and a scatter plot. The graph represents the parent-children relationship among runs. Each node of the graph represents a different run. The scatter plot shows how similar the performance simulations are considering the predicted precipitation volume, with each simulation represented by a 9-dimensional feature vector projected in 2D using PCA. There is a temporal analysis panel to enable the time-based analysis of simulations, which comprises a collection of line charts and a sunburst chart. The line charts shows the simulated value of different atmospheric fields at each time step. The sunburst chart is a collection of concentric circles representing different time aggregations, and is colored based on the accumulated precipitation in each period. Finally, the Spatial Analysis panel allows the analysis of the distribution of atmospheric fields. It contains 3 maps to visualize different fields at a given instant. The user can control the time reference used to build the maps using the top menu, and, in the case of the rainfall field, using the sunburst. The last interface view is the ensemble view, which was designed to enable the temporal and spatial visual analysis of dynamically constructed ensembles, regardless of the number of members. It contains a top menu, a temporal, and a spatial analysis panel. It uses the same spatial visualizations provided in the simulation view. The only difference to the maps in the simulation view is that it aggregates values of multiple ensemble members. We did it since using similar metaphors facilitates the experts' interpretation of results and increases their engagement with the system. They can explore worst and average scenarios by changing the aggregation function. The temporal analysis panel comprises a collection of heat matrices, one for each atmospheric field. Each row of the matrix represents an ensemble member, while each column is associated with a time step. The color of each cell is mapped to the aggregated value of the simulated atmospheric field over the domain. Using the matrices was important to enable the visualization of multiple ensemble members simultaneously while still encoding the global ensemble patterns. To demonstrate ProWiz, we performed two case studies of rainfall events in Brazil. In one of them, our partner weather experts used the system to configure, execute, and evaluate WRF forecasts of an extreme rainfall event in 2011 in Maricá, Rio de Janeiro state. Please check the paper to find the second case study. In the setup view, the experts configured the first simulation entering the start and end date, and the Corsair domain's spatial resolution on the top menu. Then, they defined the three nested domains. They frequently checked the domain summary table to ensure the nested grid's resolution and the central point were correctly determined. Next, they selected the physical process parameterizations, the source of initial and boundary conditions, and started the simulation by clicking the Run button and defining its name. Then, they were directed to the simulation view, where the simulation is represented as the root node of the run's overview graph, and they could check the first results in runtime. In the temporal analysis panel, the expert could identify that some atmospheric variables indicate the occurrence of an extreme event between time steps 18 hours and 36 hours. They closely inspect this time interval by brushing the sunburst visualization and observing the accumulated rain spatial distribution in this period. They observed that the model predicted high rain volumes in several areas of the Rio de Janeiro state. However, in Maricá, these volumes were incompatible with the actual event. Then, the experts selected specific regions of Maricá using the map. The line and sunburst charts were automatically updated to show data associated with the selection. Doing so, they could confirm that the model could not predict the event's magnitude in that region throughout the entire time horizon. On the other hand, other variables still suggested that heavy rainfall in the city was possible. The experts created 7 child runs from the root nodes, considering different physical parameterizations. By inspecting the run's overview scatter plot, no particular rainfall volume output pattern was identified on those runs. The experts created an ensemble with all simulations and, in the ensemble view, evaluated the probability of an extreme event in Maricá according to dynamically defined scenarios. They identified in the heat matrices a possibility of observing 40 mm rain between time steps 18 hours and 36 hours. In the heat maps, the specialists verified that although the possibility was relevant in some areas, it was very subtle in Maricá. Similarly, the simulated K-index values and relative humidity achieved the scenario thresholds at some regions in time steps 13 hours, but these values would only be observed in time 30 hours in Maricá. Although the simulation's results could not indicate the possibility of an extreme event in Maricá, the experts could quickly run and analyze several simulation scenarios without worrying about technical issues that should be considered if the same experiment were performed without ProWiz. During the realization of the case studies with ProWiz, it was possible to inspect multiple simulation outputs effortlessly, even when the model was running. The experts could use the visualizations to analyze spatial temporal patterns and compare the results of several simulations. According to their analysis, WRF provided false negative results regarding to the possibility of extreme events, which reinforced the need for studies to improve atmospheric modeling. Given the results and experts' feedback, ProWiz met its primary purpose, to aid weather analysis through data visualization and provenance. Thank you for your attention.